So that seems like a good idea, and I think it's worth asking whether or not it actually works.
Does it work?
Well, it's complicated.
Tell me more.
There have been some examples where things worked out extremely well. So let me just quickly summarize some of them so you have a sense. You mentioned neural networks. So neural networks, including with nonlinear connections, have been used with backpropagation in this context. Folks like Jerry Tesoro and Tom Dietrich have gotten some very nice results, creating learning systems that can actually do some fairly complicated things and some difficult tasks.
Like what?
Well, so Jerry Tesoro's work was in backgammon, and he actually used the same kind of approach in Jeopardy in the Watson system for figuring out how to do decision making. What's the right strategy for handling different situations in Jeopardy? And the value function was being predicted using a backprop net. In Wang and Dietrich's work, they were actually predicting the likelihood of success of various sort of shuttle scheduling strategies. So they were actually doing for NASA shuttle scheduling strategies.
Say that 3 times fast.
She sells seashells to the shuttling scheduling system.
Sure.
So those worked out really well. That being said, there's not that many other people who've gotten that to work effectively. I certainly, whenever I say to my students, look, these things worked so well, why don't you try it? They don't seem to be nearly as successful as these folks have been.
Hey, I got it to work for my master's thesis.
Did you really? For what problem?
For tic-tac-toe, and then for a vision problem that after I went through all this trouble, I realized was just learning round.
Oh, that's impressive, in quotes.
That was impressive enough to give me a master's thesis, which I think was the important thing. So maybe the impressive thing is that I got a master's thesis out of it.
At MIT, of all places.
Of all places.
So it does sometimes work. I find that it's kind of difficult to get it to work consistently. What happens often when my students try this is they get a system that actually tends to start to learn well, and then it goes into some kind of a death spiral because, as I mentioned before, the bootstrapping aspect of this means that you're really dependent on making solid predictions based on your previous predictions. And when they start to go south, the whole thing can fall apart actually really quickly. That being said, there's some other function approximators that actually have been more successful that are variations of linear function approximators. So Rich Sutton in particular has gotten CMAC to work on a whole bunch of tough problems. CMACs are CMAC. It's a particular kind of function representation that is like a neural net, except for that first layer isn't really learned. It's kind of decided in advance how you're going to break up the input space. And so it really is kind of just a generalization of straight up linear. These can be really effective, but they don't generalize very aggressively. And that's part of what makes them a bit safer to use in this setting.